Okay, here's the other two problems from today. This one I called Crazy Jumping Guy because I don't know why anyone would do this, but in 1936, this dude jumped into the ocean from an airship. So I just found an image of an airship in the ocean. 120 meters above the water's surface. We're given his mass. We want to know what his kinetic energy was when he was 30 meters from the water surface. And then also, what was his speed at that moment? Okay. So his beginning point, hang on a second. Yeah. Okay. I have to move far. Okay, so his beginning point is where he's jumping into the ocean from this airship, perfectly good airship, I guess. And then, so that's our first point. And our second point is where he's at a height of 30 meters. So now he's right here from the water. Okay. So if you think about it immediately, he should only have gravitational potential energy at his first point, but then he's going to have some of each at this second point, meaning gravitational potential and kinetic, because he's moving, but he's still 30 meters above the water. Okay. So if we set up some conservation of energy, we're going to have an initial potential plus no initial kinetic. That's going to be 0 because he's just standing there and then he's going to jump out. And then we've got some final potential and final kinetic. Okay. So let's include our equations. We've got m times g times h equals another m times g times, so this is h initial, h final, plus 1/2 m v squared. Okay. So we're going to solve for kinetic energy first, and then we're going to get our speed from that. Okay. So we can take, let's see, and we can clean this up a little bit. No, let's not. Never mind. We're not going to do that. All right. So we're going to do 72 times 9.8 times 120. That's his initial height above the water. Okay. Equals 72 times 9.8 times 30. That's the point that we're concerned about, 30 meters, plus his KE final. We're just solving for that value first. Okay. So we got 72 times 9.8 times 120, 84,672 joules equals 72 times 9.8 times 30, 21,168, plus my kinetic energy final. I can solve for my kinetic energy final by subtracting this number here from both sides, right? So 84,672 minus 21,168 is 63,504 joules. So he's got a lot of kinetic energy at that final point, which must mean he's going pretty fast. That's kind of scary. Okay. And then we can set this equal to 1/2 mv squared to solve for his speed or velocity at that point. So let's see. We've got 1/2 times 72 is his mass times v squared equals 63,504. 72 times 1/2 is 36. I'm going to divide both sides by 36. So 63,504 divided by 36 is 1764. And then I've got to take the square root of that to get my velocity. So square root of 1764 is 42. So he is going at 42 meters per second, which seems really fast to me. I feel like he probably hurt when he landed in the ocean. So that's why I call him Crazy Jumping Guy. Anyway. All right. Last one, we have a fish scale. Yay. So now we've got one that's going to have some spring. Okay. There's not as many examples I can find with good elastic potential energy questions, but okay. So we've got a fish scale. So it's hung from the ceiling, and we hang fish from that. So we're going to hang a fish from that, so we can figure out how much mass he has, I guess, or how much he weighs. This is a fish with a mass of 5 kilograms. He's hung from the unstretched spring and then released. So he's going to move downward until the spring is fully stretched and then move back up again. And we want to know what is the maximum distance through which the fish falls. Okay. This one's a little different because what we end up looking for here, we're looking for the distance through which the fish falls. So we're kind of looking for displacement. We're also looking for height, okay, because the fish is hung from the end of the spring. We don't know like how long the spring is in its equilibrium state, I guess. But we know that when he's hanging and he's not released yet, he's just going to have gravitational potential energy. And then when he hits his max distance, when the spring, so this is my first point, when the spring is stretched as far as it'll go, now we've got a lot of stretch in this spring, okay? So we've got initial gravitational before it's let go. Now we've got final elastic, okay, because there's a lot of potential energy that's built up in this spring that's stretched. So our conservation of energy here is going to be gravitational potential equals elastic potential final, okay? And it looks like we might not have enough information at first glance for this. So we're just going to try and put our equations in and see what we know. We've got the mass of the fish. We know what G is. H sounds like something we're looking for. And then we know elastic potential energy is 1/2 times K. We are given the spring constant for this spring times X squared. In the case of this equation, the things we don't know are H and X. And it turns out that for this particular scenario, those are kind of the same thing. Okay, they're actually the same thing because the height that the fish starts off at is going to be the same as the amount that the spring is stretched from this equilibrium point, okay, from that relaxed, unstretched point. So I could almost say M times G times X equals 1/2 KX squared. Okay, I'm really, in this scenario, my displacement of my spring is going to be the same as my height that I started off at. So I could divide both sides by X because I've got it on both sides. I'm going to end up with M times G equals 1/2 times K times X. I'm solving for X, okay? So let's see, I've got 5 times 9.8 equals 1/2 times 200. That's my K value times X. So let's see what we get. We get 5 times 9.8 is 49, and then we're going to divide that by, I know that 1/2 times 200 is 100, so I'm just going to divide by 100, and that gives me 0.49, and that's going to be in meters. So the fish is going to fall through a distance of about 1/2 of a meter till the spring is fully stretched. And then after that, it's going to move back up. But for the purposes of this problem, what we were concerned with was what's the maximum distance through which it falls. So from unstretched or from equilibrium point to fully stretched based on the fish hanging from the spring. And that ends up being 0.49 meters. All right. Hopefully that made sense.